I'm super excited to have Dr. David Mohrig to present for our first discussion hour. A quick biography. Dr. David Mohrig received his BA from Pomona College and his MS and PhD degrees from University of Washington in Seattle, and then later hold postdoctoral positions at St. Anthony Falls Laboratory at the University of Minnesota. Worked nearly for 5 years at Exxon Production Research Company in Houston, and then 2001 moved back into academia for a short time at MIT, and then finally 2006 coming to the great land of Austin, Texas, to work at the Jackson School. And he currently holds the Peter T. Fawn Centennial Chair in Geology. David's broad research uses transport processes and sedimentary deposits to unravel the evolutions and submarine landscapes. Please welcome David.
Well, thank you everyone for coming. And thank you, Michaela, for pointing out that no one had fallen on the sword for the very first discussion hour of the year of the term, and I was happy to do that. So what I want to do today is to share with you an adventure that I've been going on to do with complicated sediment transporting flows. And in this case, it's a turbidity current. We'll talk about what that is runs through a surface wave field and the consequences of that in terms of depositional patterns and the types of bed topography and sedimentary structures that are produced. We're going to do this largely in the lab because I will argue there is no numerical code that can actually do this yet. I mean, it's a multi-phase, multi-flow field problem, and we don't have the accurate enough codes to do this. I mean, and that's partly because we don't know what we don't know. That's going to be a theme of some of what I'm going to be sharing with you. But it is now, we're getting enough experimental data to help guide the development of those numerical codes. This exploration of propagating shallow wave signals into deep water is motivated by this outcrop that I went to first when I was a graduate student at the University of Washington. And what it shows are some very symmetrical ripple forms. A lot of people would call these wave ripples, and then thickening, thinning, fining, coarsening, rhythmic-like bedding on top of it. And both of those things led people to say these must be a tidal deposit associated with an estuary or some very shallow marine environment. But the broader scale stratigraphy says that we're on the upper continental slope. So we're not even on the shelf. And so there was this paradox. And the question was, well, okay, we have a wave signal in here and even a tide signal, but are there ways to propagate those signals from the water surface into the deeper ocean? So that's what we're going to be exploring. And I've done this with lots of people. I was adding up the people. They were roughly in chronological order, but then it all fell apart. But they're like 34 people that I've tortured with my passion for this question over 30 years. So, and it matters. I was giving you we'll look at those Eocene rocks in Oregon at the end of this talk. But it's also a very big, high-profile thing. So here's a paper that came out in Nature in 2005 associated with the snowball Earth. And they were looking at these large ripple-like forms. This is a cartoon of what they saw. And this is situated in their stratigraphy in deep water. And so the only way they could understand these were to have hypercanes, superstorms. So, of course, Precambrian geologists love to do this. They love everything to be more complicated than it is today. And at least that's totally my bias, but I think it's fair. So they wanted extreme winds and waves, and the question is, well, maybe there are other ways to do this that don't require having the surface waves impinging down to 150 meters. So we're going to look at turbidity currents first. And so this is a cartoon of a turbidity current. We're going to watch a movie of one in just a moment. This is the bed. Here we have the current punching its way through. So this is a mixture of water and suspended sediment. And that mixture is slightly more dense, and by slightly, usually less than 1% more dense than the ambient clear water. and it literally punches itself through the water. So it actually forces water up and over it. And that induces mixing here. So when you look at the velocity field and the vertical, the velocity goes up like we expect in an open channel flow, but then it reduces and it even goes partly negative because of course you're forcing flow up and over this material, over this you're forcing ambient fluid up and over the flow. And the sediment concentration sort of decays exponentially up with distance from the bed, which is the source and the sink of the material. So that's fairly easy to understand. So what we want to look at is, so this is fairly well understood in still water, but we want to put this into a wave field. And if for those who haven't thought about wave fields much, here's my surface water wave. You set up an orbital velocity field that the magnitude of the velocities decrease as you go with depth, and deep water waves, of course, you don't have the effect of the waves at the bottom. Shallow water waves set up a reversing current right at the bottom. Those are cartoons, but here's actually a long exposure imaging of that. They put in particles and then reflective particles, and you can see the orbital pathways that those neutrally buoyant particles are traveling. And as you get down near the bed, you can see they go from more spherical to very elliptical, and then finally just back and forth at the bed. So what happens when we take this and run turbidity currents through it? Well, if you don't know anything, the first thing you might assume is, well, we just have we're just gonna superimpose these things. We're just gonna add these two fields together. And there were papers that came out about 15 years ago that talked about that and said, well, if you have some wave field and then you have a unidirectional current, you'll either get a pulsating current that will move fast when the waves and the current positively interact, and move less quickly when they're in opposite direction, but they're always moving forward. So they're sort of lurching forward in this case. Or you may actually get a straight up reversing current that goes one way and then goes back the other way. We're going to mostly focus on these pulsating currents because we want to get sediment way out into the deep ocean, and we're not going to do that with a reversing current very well. So let's watch a movie of what actually happened. So this goes slowly. This current is not moving quickly, but it's really worth seeing this. So here's the snout of the current coming down, and this is without waves. And so hopefully you can see the snout coming down. You can see it's actually riding up over the bed itself, and that's because the dynamic pressure that is associated with accelerating the ambient fluid out of the way is sufficient to actually peel the current right off the bed and produce an effect like a car tire hydroplaning. So we have it coming down slowly, and what we want to start looking at is the degree of mixing that we see at this interface. So at that shear interface, you start to produce a lot of instabilities. The classic ones are Kelvin-Helmholtz instabilities, and that mixing produces a turbulence that is at the scale of the vortices associated with that mixing are at the scale of the flow. And here now you can start to hopefully see some rotation happening. We'll watch a couple of these. Hopefully you can see that rotational component of the current happening. And in just another few tens of seconds, I was going to superimpose anticipation onto this video because I couldn't figure out how to speed it up. So I thought we'd have some songs. But here, you'll start to be able to see some rotation. And very shortly, we just turned on waves. And what happens now is that all that mixing stops. And that was not what I was thinking was going to happen, that we were going to lose all the evidence of the mixing. You can see the pulsating flow, but suddenly these large vortices that are mixing ambient fluid into the current have been shut off. So we want to think about why that is and understand what's going on. So that's where we're heading. We have all kinds of tools. Anyone who wants to go to the lab can come do this. We're going to be looking at both data from an acoustic Doppler profiler and from a profiling ADV, which allows us to get the turbulence statistics better. Yes?
Sorry, you said you turned on waves and then
Yeah.
it sort of froze the pattern.
Yeah.
What do you mean? How do you turn on waves?
With a wave maker. So if we,
So there's like a paddle at the top.
yeah, there's a paddle.
stationary,
Yeah.
And then you kick it into gear.
Yeah, and I don't know what I did.
All
Oh,
right, I
man.
learned everything.
Yeah, well, there's a wave maker, so we turned on the wave maker and made it happen. Then we'll measure the information by moving our profiling ADV, our profiling acoustic Doppler velocimeters and our more profiling velocimeter as well throughout the system, and we can then also look at. Now we're gonna. We have different tools that we use to directly sample the current, to look at what the suspended sediment or salt concentration is. If we're doing mixing experiments, we use the acoustic Doppler shift of particles in these flows to actually get the velocity profile. We also can do that using particle imaging, velocimetry, and we use videos to get flow structure in a lot of ways. We use distancing lasers to get a sense of how the bed topography is evolving. And of course, we can directly sample the bed itself. So we have all these sort of tools available to us. And we also use acoustics to look at these systems as well. Now, I just want to remind everyone that to fully describe a complicated flow field, there are three components. And so you have some total, this is the instantaneous velocity, but that velocity has an average component, or most importantly, a deterministic component of the velocity field. It has a stochastic component associated with turbulence. This is for a turbulent flow. For a laminar flow, you could get rid of that. And there's a periodic component to this. So I've taken the periodic component out of my beautiful time series that I've drawn here for you. And you can see the mean component of the velocity here. And then all these departures are the instantaneous variability in the velocity field associated with the deviatoric velocities of turbulence. So we want to ultimately look at all those things. And I'm going to do this chronologically. So here's the first experiment that we did. We have this is from the acoustic Doppler profiler. This is the undercurrent right here. You can see the negative velocities because the water was actually being forced up and over, and it clearly set up a little bit of circulation in the tank here that you can see. So this is what it looked like. The blue line, or the bottom line, if you're colorblind, that was the bed. And then after the flow, this is the top of the deposit. So you can sort of look to see where the deposition happened and how much of it happened in one place. So that was for just a simple turbidity current. And now here's what happened when we ran that exact same input conditions under a wave field. You can see there was some erosion up in the shallow part of the system, but the amount of deposition in the sweet spot of deposition was absolutely translated down the system some. And so now we're still looking at the mean component, the deterministic component of the velocity, but I'm showing you this at 3 different times because there's to give you a sense of how that velocity profile is changing as a function of the period of the waves itself. So, though we've run this in a number of different configurations, and what we always find, so this is a plot. Now, here's our wave maker here. We're introducing the currents here. We're making detailed measurements in here, and that's actually where this data is from. And the dashed lines are showing you the accumulated volume of sediment over that particular distance. And what you can see is that in the case with no waves, and the solid lines are the cases with the waves. This is for a low discharge case. This is for a higher discharge case. The the case with waves always puts more sediment further down the system. So the currents, and these are all very strongly depositional currents in the lab, but for the combined flow currents, we're always getting more sediment further out into the system. So the question was, why is that actually happening? And the first hypothesis we had came out of just asking the question, testing this idea, are these two flow fields just simply additive? Is it just a linear addition? Well, and so we took a number of our instantaneous velocity fields and just collapsed them around zero to see what we got. And what we found was that for the upper part of the undercurrent, it does, there's a remarkable similarity in the structure. So, but if you care about moving sediment around, you really just care about what's happening down near the bed. And you can see down near the bed that there's a wildly different amounts of shear associated with the velocity gradient. In some cases, a lot of shear, in some cases, less shear. And our first hypothesis was, and so that gives you different strain rates down there. And of course, it's the velocity gradient squared that scales the production of turbulence in that area, which helps support that suspended sediment. And the first hypothesis was, well, we're getting some really high strain rates down near the bed, and that extra turbulence was actually supporting and suspending the sediment and getting the sediment out further. It turns out, when you make a hypothesis, you have to be ready for them to be wrong, and ours certainly was. And you'll see why in just a minute. But and it goes back to that movie that we just saw on the shutting off of the mixing. But a couple questions that came out of this so far, what's going on when you have a wave field present that allows the bulk of the sediment to be shifted downstream or downslope when everything else is equal? Why is that actually occurring? And is there a signal of the wave field that's being translated below wave base? And the answer is it appears so. And then what are really the mechanisms influencing the currents? How are the waves influence the currents? But if you can put a wave field into the current, then you could produce wave-looking structures at much greater water depth. And as someone looking at ancient deposits, and ancient might just be early Holocene, then that makes that you could have a very wrong interpretation if you don't start to recognize that there are clever ways to do this. So we need to look at that. So here's on the next experiment. This is the wave field proper. So there's a sloping bed in here that's 8 to 9 degrees. And what you're looking at here is the many versions of the wave field. And you can see the dashed line is actually the blue line the dashed line is supposed to be where we're actually collecting the data. And the blue line is a predicted exponential decay of the orbital velocities. And the dots are the actual average root mean square velocities. And the fits are pretty good, not so good in the true shallow water area, but there's now, you're starting to interfere with the shallow marine environment. So this is breaking down a little right in there. It's pretty good in here. You may ask, why are these big gaps here? And that's where the noise got large relative to the signal because the velocities are very small and there weren't a lot of seeds in the water to actually do the Doppler shifting on. So where the noise was high, we just had a threshold and cut it out. So that's what the wave field looks like, a lot like what you would predict. And this is what the currents going through they're doing. So the biggest mixing in the currents are associated with the Kelvin-Helmholtz instability at this shear interface at the upper surface of the current undercurrent that's pushing itself through the ambient fluid. And you can predict that, you can actually measure it directly, but I didn't have time last night to do that. So I just went to the old Struhol number, which is not a bad way to estimate this. So this predicts, it gives you a good estimate of the period associated with vortices that are being shed. It's a dimensionless number that comes out of the, right out of the second, the Navier-Stokes equation, or the second law of continuum mechanics. You have a length scale, you have a velocity scale, and you have a time scale. This is it's a good dimensionless number. It turns out that the Struhol number for an incredibly wide array of systems it's not exactly one that would make it a perfect dimensionless number, with one behavior on one side and another behavior on the other, but it's order one, and it's about 0.2. So if you take the thickness, the length scale is the thickness of the currents, the velocity scale is the mean velocity for the currents, and I want to know what the period of associated with these largest mixing turbulent eddies are. And it's about 3 seconds in this system. Now we hit that with a wave field where the period was about 1 to 2 seconds. It was like 1.5 actually seconds. And what happens is the following. So in the black is the actual data that we measured. In blue, we took we extracted the wave signal using a 5th order Butterworth bandpass filter on the frequency range that we measured for the surface waves themselves. And unfortunately, it covers up, you reproduce the wave field super well in this area and in the current. So this is right. So it's sitting there at a point. It's just in the wave field. It's about halfway down the tank. So we're not in the deepest part of the tank. The current goes underneath it. This is the head of the current coming past, so the velocities go up. And you can see a couple things here. This is the signal that's produced. In fact, we blow this up with this, and you can see the pre-current and the with current here. And if we compare the velocities associated with the pre-current, just the simple wave field, to that associated with the convolution of the wave field and the turbidity current, and run a Kolmogorov-Smirnov test, we can find that at high significance that these are not coming from the same distribution. And in fact, the velocities are always greater for our set of experiments. In these currents are amplifying the peak velocities. So we're getting a very interesting behavior of these currents when we run them through the system. And even though we're getting a signal that is amplified, we have a less turbulent flow. So this is the part now that was missing in that first case that I showed you. So what we're looking at here now is we're looking down near the bed. So if I draw, this is, what's the chance of this actually? Oh, look at that. So this is my current. And if you can't see that, I apologize, but we're looking near the bed, and we're really looking in this area of high strain rate, a very large velocity gradient, the area that should be the most turbulent in the system. And we're comparing a couple of the standard metrics that we use when we're looking at turbulent flows. And we're doing that for a low discharge case and a high discharge case in the same domain. And on top here, these upper ones, we're looking at the squares of the deviatoric velocities, dividing them by the mean velocity. And this can be thought of as a normalized or standardized turbulent kinetic energy. And so when we look at this, in the case of this is the combined flow, and this is the turbidity current alone. And again, the open symbols are the combined flow, the closed symbols are the turbidity current alone. You can see there's a minimum right there that's actually associated with the nose of the current here, because at the nose of the current, there's very little there's very little shear, because there's essentially no velocity gradient, and you have a minimum in turbulence production there, and so you have a minimum in the turbulent kinetic energy there. But we have less in the combined flow turbidity currents, even though they're moving further. And we have the same thing happening if we look at now, this is U prime, W prime. So this is looking at the turbulent or the deviatory component of the velocity field, the turbulent component of the velocity field, the product of the random variability in velocities in the primary transport direction multiplied by the vertical direction. And if you're interested in moving sediment, or if you're just studying boundary layers, this near the boundary layer area, this U prime W prime multiplied by a density essentially gives you the Reynolds stress in the system. So it's another way to characterize how turbulent these systems are. And again, the open circles or the open symbols are the combined flow, and the closed symbols are the turbidity current alone, and they're always normalized by their respective mean velocities. And again, they're less turbulent. So we're moving sediment further with less turbulence to do it. And the answer is probably in what we saw in that video where we shut down that largest scale mixing that we have in the currents. So if you remember my poor man's estimate for the period of the vortex shedding associated with the Kelvin-Helmholtz instabilities, it's going to be something close to 3 seconds. And the waves that we're putting in there are between 1 and 2 seconds. And these shorter orbital velocities are totally disrupting the mixing that we see associated with the Kelvin-Helmholtz instabilities. And by doing that, they're minimizing the dilution of the currents. Turbidity currents are interesting in that they only move as long as there's suspended sediment in them to keep them in excess of the density of the ambient fluid. And the biggest way to kill them is to mix in ambient fluid. So you slow them down, and then that sediment drops out and the current is dead. And in these cases, we're getting things propagating further down our short system, because for reasons I don't fully understand now. In fact, we have a fluid mechanicist from the University of Hull coming to visit tomorrow to see if he can help me understand how these waves are interacting with the instabilities developing along this shear layer right here. If any of you understand that, I would be thrilled. I don't, but there's no doubt that it's happening, and it's allowing these currents to put sediment where we weren't expecting it. And when we look in the bottom of these channels, we go down the system. So we're now in the deepest flow. We go from things that are combined ripple-like shapes. And why are they combined versus just unidirectional? There's a lot of work about how the curvature at the upper and the crestal zone that can separate out the combined flow bed forms from the unidirectional flow bed forms. But they look combined there, and then at the very distal end, they look like wave ripples, fairly symmetric ripples there, but they're not wave ripples, and that sediment was clearly brought down by the underflow. So we're getting something that I could give the 10 out of 10 marine geologists and sedimentologists would look at this and say, oh yeah, these are just classic shallow water wave ripples. But they're much more interestingly complicated than that, because we're getting that signal in the current, and then that is affecting the depositional patterns down the system. And so I want to spend a couple minutes then going back to why I got on this trip to start with, understanding this. And I wanted to look at what happens, where do these currents pick up this surface wave signal? Well, if you have a deep failure, many at UTIG here study failures along the continental slope today. Well, they don't have or they except in very rare storm and perhaps tsunami cases. The pressure different, the wave fields probably don't affect the stability and there's no reason why a turbidity current was unleashed that way would have any significant amount of wave field associated with it. But a lot of these currents start out where rivers come out into standing bodies of water. Here's a classic one. This is the plunge interface here. The turbid water is beginning to just plunge beneath the clear water. And you can tell that because these funny looking pods here, this is all the floating wood that was moving with the buoyant wood that was moving with the current. And of course, the current plunges and all that wood is just sitting there with no velocity and collecting. So we want to talk a little bit about what happens when a river is providing the turbid water that makes the turbidity current, because it's probably the most likely way that we get these kinds of flows. I did a lot of work with this with Mike Lamb a number of years ago when he was here as a postdoc before he went to Caltech, and there was a lot of talk about hyperpycnal flows and about rivers delivering sediment into deep water, because Thierry Mulder and Jaya Savitsky had written a paper saying, well, all you need is the suspended sediment concentration to be more than like 1.6%, and it's denser than seawater. So let's just look where it's 1.6%, and we can say all these things probably produce hyperpycnal flows, those ones that plunge. I was convinced that wasn't right, and so we because the system is much more dynamic than that. So we made a really simple 1D model that took in all the relevant hydraulics to understand what actually controlled that plunging. And this is a cartoon showing all these different these zones that you have to take care of. I mean, you have to have normal flow, gradually varying flow, a depth limited plume, and then you have to have a plunging dynamics. It's actually surprisingly complicated even in a 1D model. And this is a model result showing what the velocity does in this particular case. It's important to realize that the mechanics here actually make a filter, so the history of the river flow is not perfectly recorded in the turbidity current, though many people try to use the hyperpycnal flows to say something about the ancient river discharges. There's a filter that goes on in this plunging zone that needs to be added in if you want an accurate interpretation. So we had a model and we wanted to test it, and so we ran some experiments, and this is the depth limited plume part. Here's the plunging point. You can see it plunging down now here as a turbidity current. And what we rediscovered was what engineers had known for a long time, who study sedimentation in reservoirs. Hyperpycnal flows are incredibly common, these plunging flows, in terms of sedimenting reservoirs. So they had done a lot of work on this. And had shown, though hadn't used it the same way we wanted to use it, that it's this interface is incredibly dynamic, and it depends on the velocity of the entering jet. Really, it's the river comes in as a jet and transitions to a plume. It depends on the excess density of the system and the thickness of the system. But basically, the flow has to decelerate enough that the gravitational instability associated with gravity acting on just that little bit of excess density dominates and drives it to plunge. And in the process of plunging, it actually accelerates because it's gravitationally collapsing, which is pretty cool. And so we were able to reconstruct what the theory had shown, and then come to the point where we looked at the sediment and the sediment concentrations and the grain size. And what you find out is that in the depth limited plume case, you're getting deceleration to the point where gravity dominates and actually it plunges in. All during that time, you're losing, because it's an expanding plume, right? It's a decelerating system. Sediment is leaving the system. So these hyperpycnal flows are always a competition between how quickly it's decelerating, how quickly the sediment is coming out, and do you actually reach the plunge condition beforehand, before it actually becomes too dilute and it just never plunges and it just sits there as a homopycnal plume filling the whole water column. So the Mulder Savitsky condition, it's certainly necessary. You need to have an excess density greater than that of seawater, but it's far from sufficient. Under many cases, you need much, much greater sediment concentrations. So their paper almost certainly vastly overestimates the amount of these types of currents happening today. So necessary and sufficient. So let's look at a little bit at what happens with the tides. Do I have? Yeah, I have time. So here now is this is my hyperpycnal flow. Here is a mouth bar at a channel that is failing from time to time, producing turbidity current. Both of these are in shallow enough water where you can get the wave fields. But what are the tides? If you have the waves, you also have the tides, and what happens in that case? And of course, these deposits had two things. And in most of these coastal systems, tidal effects have a profound influence on the daily sediment transport in the system. And here's just an example of that. We have this data is taken where the blue dot is here. And so this is at high tide. This is an example at low tide. And this is what happens in terms of, this is gauge height. And this is the mean velocity at this site. The water levels go up. As the water's levels go up, because the tide, it's not a reversing current, but the tide is working against the river flow. And so you have low velocities, they stay low during the high tide. Remember, the Gulf of Mexico only has one high and low tide a day. It's an unusual system. But as the tide falls, that combination of the prism being relaxed and being flushed out to sea, plus the river discharge, increases the velocity almost 700 times. And so this has a profound effect on the sediment transport. Again, here's this is the water level gauge right here. And here is what we calculated and then measured down in here and then up in here, the suspended sediment moving. And during the rising tide, the value is 10 to the minus 4 kilograms per meter per hour, basically trace. It was just at the threshold of detection, but it was incredibly small. Then if you look at what happened during the falling tide in this area, where the sediment goes from not moving to going right into suspension, because we're looking at a very fine sand, it goes up over 1,000-fold. So now we're getting over a kilometer per meter per hour. So this is a lot of sediment being moved at certain times in much less sand, and this is the sand component. There's always some mud moving in the system. So what does this do to our currents, our hyperpycnal flows? Well, this is the same plot. Instead of the wave field, I've now made this the tides going on land and offshore with the prism going in and then relaxing and coming out. And this is my turbidity current. And we get this sort of pulsation. And you can see that in both of these deposits that are from this area where we were arguing about whether these are estuarine deposits or upper continental slope deposits, we're still arguing about it. My colleagues, honestly, many of them do not believe, because this is new, and the sedimentary structures used to identify environments have been around for a century. So it's an uphill battle. But hopefully you can see this coarsening lightening, which is actually, as you'll see in a minute, associated with coarsening. Well, this whitening and darkening that's associated with coarsening and fining of the deposits. And in both of these cases, here we have wave ripple-like deposits that are actually just vertically aggrading. And here we have more combined flow ripples that are migrating, as the bed aggrades in this area here. So this is the area where we've been. Some of you went on to this area just in November. This is Eureka Cove that we went into pouring rain, way too slippery at that point. We didn't do it justice. And then this is the area we couldn't go because it was quarantined because of some communicable sea lion disease. But we're gonna look at the pictures of there. So we're gonna look at these areas. We're looking at Middle Eocene deposits. We're in Southwest Oregon right here. Very complicated tectonic area. We're looking in the Eocene. There's still a lot of debate about where this actually was latitudinally at this time. So we have superb exposure along the coast, but the larger scale connection of this to the continent is something that many still debate. So, but if you go to the outcrop, you can see these thin bedded turbidites that look pulsating. There's a big wedge of sand, and then it's sort of diminished, and a big wedge of sand diminished. So there's something that looks pulsating like in these currents. And if you walk, that deposit is right down here. If you look, here's a big slump scar associated with the continental margin. I don't know who that is. It looks like it's waddling, so it's probably me. So there I am for scale. So these huge slump scars that are then filled with turbidites, and sometimes have actually submarine channel deposits right in the base of them. So there they are, and that's the deeper area. And then this is the other site. So site 1 and site 2, you can see them from each other. And at site 2, there's an unconformity. I think it's the continental, it's a low stand to sea level, and the non-marine system comes all the way out to the shelf edge and produces an unconformity that you see right there. So if we look at these rhythmic beds, which are coming from right in there, and we count a lot of them, and we did this in a lot of places. I took my whole research group out there and we counted beds for days. There was a really good microbrewery nearby, so they knew there was always a reward at the end of the day for counts. And so this just shows some, we marked them off after we counted them because we didn't want to lose track of where we were. And so you can see they go up and down and up, it looks periodic. And in fact, if you take just say, well, I'm going to take a 28-day lunar cycle and just superimpose it on there, it's pretty impressive. Of course, that's me fitting by eye. Remember we used to be able to publish papers that it said this trend line is fit by eye? Yeah, you can't do that. Why am I looking? Because you're distinguished enough to remember. Is that right? So we can do a spectral density estimation and look where the power is, at what frequencies, and the high power is the dark blue. The light blue is would be a 28 bed period, and if you assume each of those is a daily thing, you can reconstruct that. So they do look a lot like a lunar cycle, that we have a tidal influence there and the spring and neap tides associated with bed thickness there. That's the hypothesis. But I want to call attention to this. Jim Buttles was saying at the end of the room, I think, took this picture in highly depositional areas, and we use these tidal lights to get a sense of how the moon has moved relative to the Earth, and look at the length of a month and how it's changed over deep throughout all of Earth history. And we just look and we say, well, they look continuous, but it's really, really hard to see short-term time gaps in an environment that's strongly deposition. So I think it's necessary if you find it and you say, okay, I'm getting the lunar cycle, a signal of lunar cyclicity out of this, but it'd be really good to have some other confidence or other mechanism to convince you that you don't have time gaps. And that's why this is here. So these are climbing ripples, and you can see they start out climbing more at a lower angle, and they're stoss or upflow erosional, and then they just grade vertically as they climb. And how many depositional events do you think there is there? I mean, it looks remarkably continuous, right? Yeah, and each one of these white, dark, each one of these is an individual individual events separated by days. And they're like 30, almost 30 of them in this particular plot. So it's really tricky. And the reason why it's so tricky in these strongly depositional areas is because you can think of it, it's like kinetics. As the flow starts bringing stuff in, there's often a little bit of an acceleration, which is tied to erosion, but it takes real time to get significant sediment off the bed. And if you go into the depositional conditions right away, then you're gonna have all you're gonna see is just complete superposition of the deposits with really no evidence of the erosion. So you want some other sedimentological evidence. So this, you can tell me whether you like this or whether you hate this. This we'll take a vote. But so this is the most expanded rhythmically bedded section that we have. And this is a far back view. This is a close-in view. And what you can kind of see in both of these is that there'll be really obvious fine intervals, and then there'll be sort of a weak interval in between. And you can see that in here as well. Here are the obvious breaks, and then there seems to be something lesser going on right there. This is what the tidal tides look like in Eastern Oregon today. So I don't know what they were like in the Eocene. And the configuration of the continental margin may not have changed that much. But if you look, you have one primary low and high tide, and then a secondary low and high tide. And that, I will argue, is consistent with that being a primary low, that being a primary low. I mean, that being a primary high, that being a primary high. And then this is that little secondary bleep in the middle there. So if that is true, then this does look like we have remarkable preservation of a record here. Just to show you, this was we looked at bed thickness, but you can also look at grain size. I also made the group collect each of these beds, and we did grain size analysis on each of them. And so this is 40 beds here, so a little. So we're going from what we're interpreting as a spring to neap and back to a spring tide. And then if you look at the D90, the coarsest material, the median grain size, and the finest material, you can see that there's also an effect of the interpreted spring neap tides in these deposits themselves. And we also went to town and looked at the individual days. So now, rather than that being 40 individual beds, we're looking at 7 centimeters here, basically, and we're looking at individual, and we're doing, these are thin sections, which we used image J to do a processing on the silt to sand size, and we could get distributions estimate grain size this way. Again, the black is D75, so I changed it. This is the median in orange, and D25 in the light blue. And you can see that they also show this change in grain size. And interestingly enough, the spring to neap change in grain size is about the same as the daily change that would be associated with the rising and the falling tides. So we have sort of a nested cycle of grain size variation happening there, superimposed on the bedding. So now you can see what probably is the rhythmicity with the wave looking ripples, that the stratigraphy tells me this, the local stratigraphy is pretty clear that, in my view, that we're in at least 150 meters of water. So that would be well below wave base. And but the rhythmic bedding and the water surface waveforms have led this to be interpreted as an estuarine deposit. So clearly, something has to give. I think what has to give is that we have to recognize that these turbidity currents can translate signals into places where we didn't expect those signals to be seen. and then leave it in the form of the deposits themselves. And both title records, which have been much less controversial, and the wave field record as well. But we still need to do more. Our laboratory experiment our equipment is such that we have a limited range of current velocities and orbital velocities that we can achieve in wave periods, and therefore Kelvin-Helmholtz periods, which have to do with the thickness of the current. You know, we don't have a lot of space to work in the lab, and so at some point we do need a numerical modeler to now take this and start to understand it, and then apply it across a range where we're looking at these different velocities and how they're interacting, and how these periods are interacting, to really understand what's going on. So while I think we now know that we can get these wave signatures into the deep water, all the conditions, you know, it's possible that we just found in the lab the sweet spot and we don't find it in other places. But we have found it, at least in some cases, and need to look in others. So I'll stop there, and thanks for your attention.
Questions in the room?
Yeah.
Thanks, David. It's really fascinating. Just like, uh, in terms of the interpretation of these as daily cycles back in the beginning, really fascinating. I just wonder, did you consider other possibilities for like the time scale that these might of what you might be seeing? And it seems to me that if that's how much sediment you're accumulating over the course of a month, and you're in 150 meters of water, then we've run out of accommodation space pretty quickly.
Right.
So what
Right.
is the
Yeah, so what gives? I mean,
Yeah,
so that actually is a great question, and it's one that stratigraphers right now are arguing a lot about. I'm of the camp, and we have a review paper that talks about this, is that most of this sedimentary record is made up of what are pretty close to ordinary events. And it's all about whether that local accommodation space is available for that material to fill. So that in my view, so you have two things that can happen. You can have deposition, and then you can either keep depositing and then have a big erosional event, or you can have deposition and big periods of stasis, just straight up stasis. I think most of the stratigraphic record is sort of closer to business as usual, and then a lot of stasis, and then more of this. So you set up the template, and the topography evolves for long periods of time, setting up locations that then accommodate what is commonly more normal sedimentation than we would expect. It's not that you don't get extreme events in the record. The sedimentary record is not made of extreme events. It's mostly made out of normal events, I think. And you can read our paper and decide whether you agree or not. I mean, this is another thing that we have, you know, real debates about, honest debates about. Yeah.
So it really depends on the period of your waves relative to the size of your turbidity.
Currents, yeah.
So on your point, if you need such specific conditions, is it really an everyday thing? If it just happens so much that your turbidity current happens to be exactly the right thickness for the waves to.
Yeah, so it's a great question. We just don't have a lot of flex in the lab, but we scaled everything at 100-to-1 scaling. So, and this is what we got. So, but your question, we need to explore this under a wider range of these what I think are these controlling fractions here. Our scaling suggested everything was sort of in typical of typical water surface waves and in the environment where they'd be interacting in the shallow water. But we weren't able to really tests the limit. So we don't, I can't, you're right, we may have just hit a sweet spot. I don't think we did, but I can't prove that. That's just belief, yeah.
Thank you.
Sean has a question online if you want to unmute.
Yeah, great. That was an awesome talk, David. I guess my question may be following lines of the last couple. What's the, if you will, the preservation potential, or how special of a situation do you have to be to not have these kind of deposits get wrecked? Do they have to be especially thick, or some other condition that preserves them over geologic time, do you think?
Yeah, I think you need to deposit them in what at the time was a relative topographic low. And one of the things that a number of us are trying to understand is what is relative topographic low mean? How low is that low topography? I don't think it's not like a moat, it's just low. Like if you could scale things by a channel depth, it's like if you could get it lower than a channel depth, you'd probably be, you'd be in you stand a good chance of this being preserved. But that's something that we're actively working on right now.
And that has a prediction then that these would be sort of isolated pockets, if you will, in a given landscape.
Yeah, but these lows can be big. So these pockets could be hundreds of square kilometers, or they could just be meters. But yes, that's right.
Yeah, makes sense. Awesome. Thanks.
You know, Sean, if you look at the seismic data from the Gulf, we have all these beautiful river channels that are preserved for tens of kilometers or more. There's absolutely no way that should work, given that the combined subsidence rate is like a hundredth of a millimeter a year. There isn't enough time to take that out of the zone of erosion. So we've actually gone looking for what's making low topography in the coast, and you know, that's that paper that John put out in Nature Geoscience, which I thought was you know what was producing that low topography. And in that case, yeah, it covers hundreds of square kilometers.
Yeah, awesome. Thanks.
We are at time, and I'd like to respect everyone's time this afternoon. So let's thank David one more time. And a shameless plug, because I'm co-organizing the symposium. If you have grad students, please get them to sign up and present. And if you would like to be a judge, please come talk to me to judge. That's all. Thank you.
And you have undergrad students too, right?
Yes, undergrads, high school students, everyone.
Yeah.
Thanks.